wondered why a massive gravity hole exists in the Indian Ocean, seemingly defying the laws of nature? It's a question that has baffled scientists for decades. But now they believe they finally cracked the code. Let's dive in. Imagine an invisible water level that Earth maintains, known as the geoid. If gravity alone shaped our oceans, the surface would mirror this geoid perfectly. However, south of India, something strange happens. The geoid dips dramatically. At the heart of this anomaly lies the Indian Ocean Geoid Low, IOGL, where the geoid plunges about 330 feet, 100 meters below the global average. This begs the question: what forces beneath the surface could carve out such a deep gravity hole without leaving any visible scars on the ocean floor? The absence of surface features suggests the answer lies deep within the Earth, specifically in the movement of mass within the mantle over vast stretches of time. Unraveling the mystery of the IOGL. The IOGL was first identified in 1948 by Dutch geophysicist Felix Andries Venning-Meinesz during a ship-based gravity survey. But the true cause remained a mystery until this groundbreaking new study. The researchers constructed intricate computer simulations of mantle flow, spanning approximately the last 140 million years. They incorporated plate movements, the sinking of old oceanic slabs, and the rise of hotter, lighter material. Their goal? To recreate the IOGL's size and shape using a realistic model of Earth's history, rather than a single snapshot in time. The simulations that best matched the IOGL included plumes that rose high into the mid-mantle, significantly influencing the gravity field at the surface. This discovery links the specific vertical reach of these plumes to the strength of the anomaly. What does a gravity hole mean? Gravity is stronger where there's more mass and weaker where there's less. The IOGL represents the largest negative gravity anomaly on Earth, making it stand out on gravity maps. Satellites, by tracking subtle changes in their orbits caused by gravity, can map these highs and lows with incredible precision. Because the seafloor in the IOGL region looks normal, the signal points to something happening deep below. In an idealized world, the ocean's surface would align with the geoid. Over the IOGL, this surface would be significantly lower than the global average. While ocean currents blur the picture in reality, the negative geoid signal remains strong, creating the gravity hole we observe today. The deep mantle's role: Africa and the Indian Ocean. The models trace the origin of the IOGL back to the Tethys Ocean, which once separated India and Eurasia. As oceanic crust plunged into subduction zones, cold, dense slabs accumulated near a hot, low-density region in the deep mantle beneath Africa. Geophysicists often refer to this hot region as a large, low-shear velocity province. The sinking slabs pressed against this deep structure, triggering buoyant plumes that drifted eastward and upward beneath the Indian Ocean. Together, the heavy slabs and lighter plumes rearranged the distribution of mass within the Earth. This, in turn, reshaped the gravity field, matching the magnitude and outline of the present-day IOGL. Timing: a history of Earth. The simulations suggest that the plumes capable of shaping the geoid low began rising approximately 20 million years ago. This time frame aligns with the expected sequence of events: slabs descending into the lower mantle, interacting with the hot African province, and eventually forming steady upwellings. India's rapid northward movement across the ocean and its collision with Asia, which fed subduction over millions of years, set this chain of events in motion. But here's where it gets controversial. Not all models agree on the exact mechanism. Earlier studies focusing on the present-day mantle structure hinted at the importance of warm anomalies in the mid to upper mantle, but the origin remained unclear. Some models even suggested the cause was located directly under the geoid low. The new research offers a different perspective, a dynamic interplay between long-lived slabs and the deep, hot mantle beneath Africa, ultimately channeling plumes towards the Indian Ocean and producing the observed low. Unveiling the hidden mantle structure. Researchers combine 3 key lines of evidence to study the hidden structure of the mantle. Gravity data reveal where mass is concentrated. Seismic waves from earthquakes scan the interior, with slower waves highlighting hotter, less dense regions and faster waves outlining cooler, denser slabs. Finally, geodynamic models test whether a proposed interior layout and history can generate the same gravity signal seen at the surface. When all 3 pieces of evidence align, the confidence in the accuracy of the interior picture increases. What's next? And this is the part most people miss. More detailed images of the mantle beneath the Indian Ocean are needed. Increased seismic station coverage and more earthquake recordings can refine the shape and depth of the plumes and the edges of the deep African province. This will allow modelers to better understand the connection between upwelling and its impact on the geoid. Why the Indian Ocean Geoid matters. This research provides a cohesive picture, connecting surface plate motions, deep mantle circulation, and modern gravity measurements. It explains why a seemingly ordinary seafloor sits above the deepest geoid dip on Earth, demonstrating how mass movements over long periods create the signal satellites detect today. The story unfolds from ancient ocean crust sinking into the mantle to hot upwellings moving eastward, culminating in a distinct gravity signature in the ocean's level today. The full study was published in the journal Geophysical Research Letters. What are your thoughts on this fascinating discovery? Do you think this new understanding will change how we view the Earth's interior? Share your opinions in the comments below.